I wanted to say a little bit first about shaping land, because I think of this from a landscape architectural perspective, that we can learn a lot from how humans have shaped land in the past and how people in different parts of the world are taking this on now. This happens to be an image from the Dutch shoreline. And I don't think the Dutch give enough credit to the Romans for teaching them a lot about canals. But this map shows, from 1750, it shows the Roman occupation of the Netherlands, what's now the Netherlands, and the construction by the Romans of a canal along here. And one of the Roman soldiers who was part of that occupation and construction of canals in the Netherlands back in 50 AD was Pliny the Elder. And I thought he gave an interesting description of the people who lived there at the time and what they were doing. But the first part of it that I liked, this is written in the Natural History, Pliny's Natural History from AD 79. And he talks about whether the land along the coast is really the sea or really the land. And I think that was a prescient thing to be thinking about at that time. We have that conversation today, whether it should be the sea or whether it should be the land. With sea level rise. And then he talked about a wretched race of people who lived on the coast of Northern Europe and built artificial mounds out of sand that they lived on up above the highest tides and floods. And I think that we need to learn from some of those historical examples. This is a terp, which is what the Dutch call these mounds that they built in flooded places, and some of them are still present today, where farmers still have land that they occupy on top of that made high land. So that's my first example of an old strategy for shaping the land that's kind of appropriate for the United States, because you build it once and you don't have to maintain it very much. And that's how we have to think about things, because in our engineering world, we don't spend a lot of money on maintenance. I'm going to take you now to the San Francisco Bay Area, and this is an older map, 1899, that showed the complexity of wetlands. This is the South Bay. This is actually pretty much right where the Facebook headquarters is, up here, and Google is down here. So a little before that. But it shows how complex and how wide the wetland edge was on San Francisco Bay when it was colonized. Since that time, we destroyed almost all of the wetlands around the bay for agricultural development in particular and urbanization. That's all urban, this gray. And then these areas are being returned from agricultural use to habitat. And it's a very ambitious program of building wetlands, of shaping land, using sediment, and opening berms that blocked the sea from entering these areas to use them for agricultural purposes. And it's the most ambitious program of its kind that I know of in the world. The goal is to make 40,000 acres, or 40,000 hectares, 100,000 acres of restored wetland over the next 20 years. So that's pretty impressive, and they're about halfway there. And we just recently passed a property tax on parcels of land where everyone's paying $12 to put in and create a pot of money that's $500 million over 20 years to finish this wetland construction process. Originally, the whole thing was done for habitat. We have very strict environmental laws. We had species in decline. This is one of those species. It's the Ridgway's rail, a bird, and its habitat is in these intertidal marshes. And that's the reason why the whole thing started. It picked up steam in the late 90s, and you see a whole bunch more wetland restoration projects being done after that, mostly on this logic of creating space for endangered species. But around the early 2000s, these studies started coming out that showed how much wetlands could reduce wave energy. Probably around 2005, when Hurricane Katrina hit New Orleans, people started to really think about this. And we found that a fairly narrow wetland could do a lot of work to reduce wave energy. And since wave energy is a big component of both erosion and flooding, that's a very significant way to buy time for sea level rise. And Back about 10 years ago, people were talking about between 40 and 140 centimeters of sea level rise around the Bay Area. And you can see in this light blue, that's pretty much all those wetlands that are intertidal today and would be submerged and less intertidal, more constantly submerged and subtidal, with only 16 inches of sea level rise, about 40 centimeters. And then this dark blue shows 140 centimeters, and that we're starting to get into a lot more urban areas. This is an airport. This is the Oakland airport. This is the San Francisco airport up here, or actually, I'm sorry, right there. And a number of cities along here, and of course the headquarters of Google and Facebook, that would all be affected by only 16 inches of sea level rise, 40 centimeters. So after we had talked about the wetland issue, we started to realize just around 2012, based on work in Hawaii, that we also have a problem from groundwater flooding. And this was pioneering work that was published in out of Honolulu in 2012 that showed that this much of the city of Honolulu would flood with a meter of sea level rise. And if they considered how much the freshwater groundwater table would rise on top of that salt water, twice as much of Honolulu would flood. And it's not an option. I mean, it's going to happen. It's not like we get to choose whether we plan for groundwater or not. It's happening. So that made a lot of people nervous in the Bay Area. And we started talking about what our groundwater is. And first there's a lot of talking. And then finally, some students and my students made a map this past summer using well data and showed all of these areas in red where the water table in a wet year is already within a meter of the surface. So what that means is, based on how geologists understand the phenomenon close to the ocean, if the ocean rises a meter, all those red areas become areas with surface water flooding permanently, or at least at high tides in a wet year. But that's a very significant area of impact. There's the airport. There's another airport. Here is Google and Facebook down here. So that's a very kind of significant kind of flooding, and several cities around the Bay Area are already, down here, pumping groundwater all the time to keep themselves from having surface flooding. So thinking about groundwater has been changing the way we think about our problem. One of the reasons why is because of surface flooding. So here's the freshwater water table, and here's the saltwater interface with that. So the bay is on this side. Even if we have a levee, and live in this kind of shallow zone above the water table, as the sea level rises and the water table rises also, that floods all of this inland area in spite of the levee. And that's really important to remember. We see a lot of drawings now for coastal development projects, housing and other kinds of urban districts, where they show a levee, but they don't show any pumps. So obviously those two things are going to have to go together. Sewer pipes can fill, especially our cracked sewer pipes. We live in a seismically active area, so our sewer pipes tend to be cracked. They can fill and not function anymore. And then areas that have hazardous material are typically soils with contamination are capped from above, but not lined from below. So as the water table comes up, it'll remobilize human carcinogens that are present in an urban soil area from old gas stations and other kinds of land uses. I just wanted to show you one place where we can see groundwater flooding already. This is a tide gate and pumping station that serves the city of Oakland at Lake Merritt. And we're looking in it from the bay side towards the inland side. And I'm going to show you something happening here at a high astronomical tide that happened this past winter. This is that tide gate. And I'm going to show you what's happening at the edge of it. This is water from the bay. This is seawater coming in through a crack. Pardon my cinematography. This is, me out there on the king tide day. That's upland. This is water coming in from the fresh water coming in from the ground. And this is groundwater bubbling up from below. So we can see seawater, water draining out of the hillside, and water coming up from below. And that's what we'll see a lot more of happening at high tides in the next decade or two. So the other reason groundwater is super important, besides the flooding itself, is our earthquake-prone region. These are the faults that shape the world that we live in. East Bay is the area that we're working on right now, and this fault is the most likely to have an earthquake in the next 10 years. An 8.0 is what people are dreading and expecting at the same time. It's come to the point where they don't say if, they say when. So we're expecting it relatively soon. This area is also subsiding. These data came out a week ago. And a geologist from UC Berkeley has shown finally from satellite data that these areas of the bay are subsiding much more quickly than anybody thought. Here's San Francisco Airport subsiding very quickly, an area called Foster City, and one of the wetland restoration areas over here called Eden's Landing have really fast subsidence rates. Just to give you a kind of quick comparison, some of those are subsiding at 10 millimeters a year, and of course over a century that's a meter. So that's a lot of subsidence that's possible in those places. And the same study showed these areas, this particular one is Foster City, and this is San Francisco Airport, would be underwater quicker than anybody expects because of the subsidence effect. And part of it is being underwater to the water table, not just underwater to sea level. We have looked at the cost of building walls, like we just saw for Melbourne. We've looked at potential positions for a new bay edge that would be defended with levees or seawalls, and the costs range from 50 billion to 100 billion US dollars just for 1 meter of sea level rise. So it's not really feasible to do it, and the walls wouldn't solve the groundwater problem. So spending all that money, we'd only get halfway, if even that, to being ready for sea level rise. And the state of California is now considering giving guidance to all of its public agencies to use a 3-meter standard for sea level rise by 2100, not 1 meter. We were already at 1.5 meters in 2009 and are now planning for 2 meters, and the state's about to issue guidance that'll take it somewhere above 2 meters and possibly to 3. So there's a competition happening in all of that, funded by the Rockefeller Foundation, called Resilient by Design. My students and I are on one of the 10 teams. And the idea is to propose adaptation strategies. And these are the 10 locations. This is my team, the All Bay Collective. We're CMG Landscape Architects, AECOM Engineering, and Urban Planning, and a bunch of other really excellent, all local firms. So we're looking at this location here at San Leandro Bay, and I have this picture up on the screen with it because this is a boat that was discovered under downtown San Francisco. There are dozens of these boats that were left behind during the gold rush. You know what I'm talking about. This is a gold rush town too, right? People were in such a hurry to get to the gold fields, they just abandoned their boats, and the city got built on top of them, including the city's seawall, which is now going to have to be rebuilt at a cost of somewhere between $4 and $5 billion, part of which just has rocks piled on top of an old couple boats. So there are surprises waiting for us underground in a very hurriedly built urban region. These are all the sites that have been assigned to the different teams. Hassel is, of course, an Australian firm. Big and One are bringing ideas from Europe, and Field Operations is Jim Corner. Common Ground is Tom Leader Studio. All these different groups are looking at locations in the Bay Area that might have important new ideas. I use this slide just to remind myself to say that what I think I have brought to this process on our team is looking at the volume of landscape from a geological perspective, not just looking at surface mapping. I was really pleased to see Nigel's geology slides, but trying to understand landscape as a 3-dimensional melange or volume through which water flows and everything else starts to happen is really key for us. This is our site, San Leandro Bay. You can see in the alluvial material that dates back to the last 50,000 years that a lot of rivers used to be larger and carried a lot more material down, and they've changed course or been altered by urban development, and all of this pink is urban fill. It's all artificial. And it was filled on top of wetland areas, but thinking about landscape as a 3-dimensional volume or section, when you look at geological cross-sections, you can see how active it is. You can see how crazy the mix of faults and materials makes this place. And this is a recent seismographic section of the East Bay that shows the depth to different aquifer layers. So this is deep. This is in meters on this axis and in meters on this axis. And they're looking for understanding what's going on with the deeper groundwater. But look at all these faults they've found. These red lines are all faults. And they do these studies in a fascinating way. It's very American, I think. They drop shotgun blanks into third of a meter deep holes, and they go along with a seismograph recording what happens when the shotgun blank explodes. But it gives us good data. And when you zoom into the area right near the coast where we're working, there's a very shallow water table up here, which isn't really shown in blue. They were looking at deeper water. But look at all these cracks, these faults. We don't know what's going to happen when those faults interact with sea level rise or with more extreme rainfall, whether groundwater will move in relation to those faults. So I keep going back to older maps and representations, trying to think about, okay, what are the surprises that are waiting for us, thinking about human strategies for dealing with uncertainty? We don't know if it's going to be a meter, if it's going to be 3 meters. We don't know how it's going to interact with the faults. We don't know what poisons are in the ground. We have a lot of sea monsters to think about. So let me show you the area we're looking at. Here it's a sports stadium site. This stadium is going away. We've lost 3 professional sports teams from Oakland. They've moved to San Francisco or to other metropolitan areas. They're all private teams, so they can do what they want. And this facility will stay. So most of this site becomes available again. This is the airport, Oakland Airport, and the airport is thinking of relocating a terminal, moving more of its functions off of the airport site so they can deal with flooding. They're in a very dangerous spot with the airport runways, and move more of their terminal and baggage handling and everything out to where a transportation center is. Out here, there's a regional rail line and a subway line. So we're dealing with that, basically an island surrounded by creeks that already flood. This is a highway with 250,000 cars and trucks going on it on average every day. So it's a lot of traffic, 8 lanes of traffic, and on an extra high tide, it's within a foot. The high tide water is within a foot of the roadway surface that services 250,000 cars and trucks. So something's going to happen soon, and that's how we're thinking about this, is conventional systems starting to fail. This is the water table, so the really shallow groundwater is shown in red, and this is the liquefaction zone, all that old wetland that's been filled with random urban rubble is very, very likely to cause failures of structures in the earthquake. And this is where we think we have, well, we know we have, contamination in the soil, and what direction that contaminant could be moving in towards the bay, typically. So as we think about adapting this site and developing it, we have to think about human carcinogens moving under the water close to the surface, and as the water table comes up, people being exposed to that, and pipes put in the ground helping to convey the vapor component of that, which is equally deadly. So what are some of the adaptation strategies that we're looking at? I'm going to show you a few examples from the Netherlands of what we think the Dutch have to offer, not what the Dutch think they have to offer, but what we think the Dutch have to offer. You have to tell your consultants exactly what you want, right? And then I'm going to show you some awkward drawings because the competition is in process right now, and some of them are student drawings and some of them are team sketches. So Amsterdam is a city that was built with a high water table. It was built with canals that were spaced to allow the drainage of the block. Obviously, there's something we have to go back and look at there. That was done in a way that allowed people to cope with living in a high water table. The canals are multimodal spaces that were excavated and then material placed on the block, and then the canals function to drain the block. There are a lot of really important old ideas here that we can use to be able to live with this very high water table. Some of the newer ideas, one of them is near Rotterdam, and it's basically to excavate a pond and then put housing in it, where that pond is revealing the depth to the water table, and it's providing some storage for stormwater. This is a marketing image, obviously. the idea was to build this, what's essentially a stormwater wet pond, a piece of public infrastructure, and then sell houses in it to wealthy people to take pressure off of the housing market for more middle-income families. What a great idea. We need to try that. That's going to be part of our strategy, because we know that educated people in the Bay Area are more likely to track what's happening. If they see a crack form here, they're going to call someone. They are the ultimate monitoring strategy for new infrastructure ideas. This is a development called Steiger Island in Amsterdam's Eburg district. And in that one, they're doing something that they didn't. In the last one, the houses were placed on pile foundations. We would have trouble doing that in an earthquake-prone region. We'd have to have very deep pile foundations, and that gets expensive. So what we're thinking about is this kind of strategy of floating prefabricated units. With some buildings, this big bar building is on conventional foundations, and so are these on this levee. But the rest of these are floating and using shared decking for what I think are 2- and 3-story row houses. So we're looking at that model. That's an image up close of what that development looks like. And the basic idea that we're pursuing is, again, landscape shaping. We're talking about digging a hole and then building up an edge, a thicker wetland edge on the bayside. So it's Rich Haig's old quote. Rich Haig is a famous landscape architect in the US. Dig hole, make mound. That's the essence of landscape architecture. I've just saved you a lot of conversation. And what we're talking about is bringing water in from the creek, but also bringing water in tidally into what's essentially a tidal lagoon with 2 gates, one high and one low, and then floating prefabricated units onto shared decking supported by pontoons. And what that might look like, here's a quick diagram. Because we're talking to the wetland community, we can't just propose putting a lot of housing in these areas. They want the wetlands that are on the edge of the bay now to move inland as the sea rises. So this is a negotiation. This is a dance. If we build a tidal pond at the edge of the bay, we'll use the material from it to enlarge the wetland, to build that habitat wedge. We'll build more tidal ponds inland on that sports stadium site and then use the fill to fill the old pond. So this is a little bit of a pyramid scheme where you have to keep digging ponds to have the excavated material to fill the old holes. Otherwise, the wetland and environmental community won't support the idea. So we're talking about how far we could go with this. And as sea level continues to rise, the idea is to move these ponds farther and farther inland. And because the housing units are prefabricated, many times steel frame, we think we can crane them out of place and relocate them in a new pond with minimal loss of value. So developers would own the units, but not own the land. And the public, a land trust, would manage the land and the site. So this is an awkward drawing. It's a Frankenstein of people's different versions of what a tidal city, which is what we're calling this pond with houses in it, might be like if we did all of them at once. And then this drawing shows what kind of landscape armature we think we may be able to get. Here's that sports site, and then this whole edge of the bay, creating an armature that supports these tidal cities. This is the airport's potential new terminals. And the idea here is to think about a kind of new emerald necklace model where we do an armature around the edge of the bay of wetlands, and then we add some beads to that of these tidal ponds that may at some point become wetlands again in the future. So those are the ideas that we're working with, and they're pretty simple. They're not high-tech ideas. They're not very mechanical ideas. There are tide gates, but that's something we kind of know how to do on a small scale. And the idea is to try to think about these new urban precincts where the water table is high and you live in it in a way that works for a seismically active region with different risks than what people would have in Amsterdam or someplace like that. So that's what I wanted to share with you about our work so far, and I look forward to the discussion.